use the Hooke's law, F equal to negative Kf to apply into our case. So the lattice vibration have wave and particle property. Okay, no, this one no problem, right? Because you have gone through the quantum mechanics. You know that for some of the quantum particle, they have both wave and particle property, just like the photon. And then phonon also have the same property. They also have wave and particle property. Okay, so we can use the wave function to represent this lattice vibration or the word phonon. So the particular property of quantized lattice vibration is known as phonon, and the wave transmission of the lattice vibration in the crystal is assumed as the motion of one or more phonon. So each phonon has energy hf or bar h omega. Okay, and also the momentum bar h k. So remember, just now I told you that you want to find the relationship between omega and k, right? Omega represent the energy, and the k represent the momentum. Actually, you want to find the relationship. Okay, in other words, we are actually finding the relationship between energy and the momentum of the phonon. You want to know how the momentum react with the energy, how the energy interact with the momentum. When we change the energy, how much the momentum will change. Okay, this is what we call the dispersion relation between omega and k. Okay, remember that one of our main purpose for this chapter is to find this one, the dispersion relation between omega and k. This omega represent energy, and then this k represent momentum. Why omega represent energy? Because we know that bar h omega equal to E, and then we also know that bar h k equal to momentum equal to mv, right? So we want to find relation between E and mv, then we can find the dispersion relation between omega and k. Okay, why are phonon important? Okay, the phonon have some very important effect on specific heat capacity, electron scattering, and thermal conductivity. Okay, so in next chapter, I would introduce you how do phonon affect the specific heat capacity, and how do the phonon affect the thermal conductivity. Okay, different material, let's say like I have wood, Gayu, I have iron, Besi, I have copper. So all these three materials have different thermal property, okay, just such as thermal conductivity as well as the specific heat capacity. Why do they have different thermal property? Because of the phonon, the atom arrangement inside that three material are different. Okay, so in this chapter, I just introduce you what is phonon, and I give two simple models to explain the concept of phonon. And in next chapter, I will introduce you how do I relate phonon with all the thermal property. Okay, so just in case if you have forgotten what is specific heat capacity, the specific heat capacity is the amount of heat per unit mass required to raise the temperature by 1 degree Celsius or 1 Kelvin. Okay, then electron scattering means that process whereby an electron is deflected from its original part. Then thermal conductivity, the property of the material ability to conduct heat. Okay, it's similar to the electric conductivity lah. Thermal conductivity means that conduct heat. Electricity conductivity means to conduct electricity or to move the electron. Okay, so remember just now I said that I will introduce you two models. Okay, the first model that I want to introduce you is a linear monoatomic lattice vibration. Okay, in here we have three keywords: linear, monoatomic, and lattice vibration. Three keywords. linear means only one direction. Okay, we know that the atom will vibrate in three directions, X, Y, and Z. But to simplify everything and to make yours and my life easier, so normally, if you look at the many textbook, they will only introduce you in 1D because they just want to introduce you the concept. Okay, the concept. So for 1D, so we only consider it as along X direction lah, easier. And then monoatomic means that it only have one type of the atom with same masses. Okay, so if the first atom is M, then the second atom also M, the third atom also M, same mass. Okay, then we have to know the lattice vibration for this model. So the objective for this section is to obtain the dispersion relation, which is the relationship between omega, the angular frequency, and it represents energy, with K, the wave vector, and it represents the momentum. Okay, we want to find the relationship between omega and K for the phonon. So we will first start from this slide. So lattice vibration actually involving the restoring force because atom and atom have interaction, and when one atom moves, the second atom will also be dropped and then be forced to move also. Okay, so you can look at this one. At equilibrium state, everything are static, and then the distance between the similar atom is A. Okay, in here we use A. However, when you increase the temperature from 0K to maybe like 100K or any other temperature, then now you see that the atom actually now moving. Okay, and different atom will have different degree of movement. It depends on the source of the temperature or the source of the heat. So this is the equilibrium state or static. This is a vibrating state. All right. So the lattice in equilibrium, like this. So in here, because all the atoms are the same type, right? All the atoms are the same type. So this is A, and then we name the atom. The middle one we name it R. Then the next one R+1. The next two R+2. Okay, the previous one R-1, and the previous two R-2. Okay, in the equilibrium state at temperature equal to 0K. When you increase the temperature, now we find that the atom actually vibrating along X, Y, and Z direction, three directions. Okay, but to simplify it, we only consider that the atom only move in one direction, which is along X direction, positive X and negative X direction. So each atom, you can see that it moves with different degree of freedom. Okay, so now the atom displaced by longitudinal plane wave with displacement UI. So the wave is along this direction. So it's actually move the atom along that direction from, you see this atom R+1 from this position to this position by the wave transmission. Okay,